Hey, camera's live. Pile in, maybe not. It's holidays. So I'm recording. This is Coffee Compiler Club. We're here to have a discussion about compilers and language runtimes, concurrency and constructors and finalizers and every kind of thing like that. Typing systems and I don't know what all. It's an open mic. Ask what you want when you want. It's all being recorded. It'll show up on YouTube when I get around to it. Generally the same day. I'm getting a little more realistic here. Since last week I was a little slow. I reserved the right to moderate, never had to do it. That's it. I guess we're all live and you know it. So if you don't like being live, bail out, which everyone knows it already. Okay, so Ludwig's back again. I don't have anything set. I've had a very busy week because for whatever reason, the land of consulting popped up big time with two large companies that are well-funded doing language projects. Both wanted me on board right away. So I'm busy. So I'm still implementing Hindley Milner and forward flow partial evaluation. And I'm up to doing the interesting tidbits around memory.
So which projects are you working on? Can you say, or is it a secret?
Yeah, probably. One of them is this company doing, well, the company is very large, it has a lot of customers. I'm sure they're public now. So it's relational.ai. They're doing an SQL replacement where they're trying to do pure description and not imperative description of your problem. You describe a relation and they're going to turn that into something they can imperative and compute.
Well, isn't SQL pretty declarative already?
Yeah, so they have a different declarative where they're really getting sort of hardcore about relations. And the language is all about doing relations. They have some interesting results. They're all over the map in performance. It's like they can either get it converted into something sensible or they can't, and it kind of, orders of magnitude faster or slower according to the phase of the moon and how well the optimizer turns the problem around.
Yeah, they're trying to write an sufficiently smart compiler, right?
Exactly. Yeah. And their constant factors kind of suck. And of course, I did this thing at H2O where I drove the constant factors on doing math down to ludicrously small numbers. And so there's something that says that we can do something and get the best of both worlds somewhere in there. It was, the typical constant factor for accessing any one element was somewhere around a nanosecond on any big throughput, which typically meant that, and all completely parallelized to the max, which typically meant that touching a terabyte of data was a thing that you could do in under a second, which meant that passes over terabytes of data with big complicated equations that had to do filtering hugely to reduce the sets down, because if you did in the wrong order, you got giant sets and that killed you, don't really matter in H2O. You're going to touch everything anyhow all the time, and it's going to be quick all the time. So it's a very different programming model. So they had that, that's that one. These other guys are doing, it's Tezos, it's blockchain folks. They're doing smart contracts. They have a forth-like language that is strongly typed and formally proven to be correct, and also correct on the safety concerns, like the volume of memory allocated and the size of the stack for recursion, all that kind of stuff is completely formally proven to be correct, because they have these contracts that you assume are going to get attacked constantly because there's money attached to them. So they're trying to make that interpreter run faster, and they have. That one's actually probably going to be easier. That one's going to be sort of straightforward, I think. But they've been getting out of.
You're there for performance.
Yeah.
Okay.
Yeah, it's a formally proven byte-coded style language. Basically, it has some weird primitives that do things like put things on and off a blockchain, and it has some weird primitives related to fixed size, not fixed, but dynamic storage allocation has some extra smarts in it because they'll bill you for storage because it goes on every block on the blockchain. There's a computational cost, so it's an arbitrary function with Turing complete, except that you paid gas up front, that determined how many clock cycles you got to run before you died. So if you don't put enough gas in, your contract won't complete. It's fine. Now, you know, this is an interesting programming model. And then they have an interpreter written in OCaml that some would claim is some distance away from being the optimal speed you might hope for. And they have no performance work done at all. Not performance, they have no profiling work done at all. So I did the 1 hour meeting and said, well, I'll bill you if it goes too much longer. And also, you know, here's my rate. And they swallowed that. And then I said, start benchmarking, folks. Just don't do any performance work till you benchmark. And I said, okay, fine. Okay, it's freezing cold and my antique cat wants to go outside. So I predict in under 5 minutes, he'll turn around, come right back in. This is the usual morning. He's in and out 3 times in a row before he finally gets enough sunshine.
Speaking about profiling, I've also had a busy week looking at profiling with regards to unsafe accesses, because we had an unsafe access in some shared code, and in some cases the base object was null. In other cases it was one type, in another case it was another array type. And basically C2 wasn't optimizing these, even though we had full inlining in a loop that only used one type for the entire loop. And after looking at this for a long time, it turned out that we were converting the base to we were converting an object from which we derived the base implicitly to an interface type. And this was erasing all the type information that we had up above that in the call chain. So it seems that C2 doesn't really handle interface types that well.
That was one of the things I did at Azul was I redid the interface work on C2 completely. And it gets, the Azul C2 gets interfaces like completely now. And I pulled them out of the hierarchical typing system for classes. So here's the cat running back in. Yeah, it's too cold for you, huh? And,
actually, there is a known problem with interfaces that you cannot trust statically declared interface types because they are not verified. And if you don't do any special verification, you are very limited in terms of what you can do with interface types.
So right. So what I ended up doing was that I mostly could convert an interface to a base type, a class that was the actual class. Like you could in fact come in with multiple interfaces, and in practice, mostly you were not. And if you came in with multiple interfaces, I gave you the base class. I kept all the exact interfaces that you had, and I gave you the base class that was the super class of what everybody who implemented the interface could be.
But the problem here is that the initial interface, where do you get the initial interface type? If it's statically declared in the bytecode, you cannot trust it.
I got it by looking at the class hierarchy after the interface showed up.
But then in the program, you have a value which you think this is interface type.
Yeah.
Where do you get the source of this will be interface type?
I'm trying to remember now, because I remember having to deal with that, and it did turn into, you took like capital O object, which didn't help you anything. But I mostly could find reasonable values for interfaces, for concrete classes for interfaces.
So
there was a bailout path for just became capital O object, and
in the C2 code, the optimization is basically if you have a check cast PP node from some type to an interface type, it will only remove a check cast PP node if the target type is the exact type as the source type. And there is a comment there about having a phi node with 3 interface types and not knowing the actual concrete implementation. And I suppose the C2 type lattice doesn't have union types, so you couldn't say each of these types together, but I'm not sure about the concrete types. So I guess that's what you fixed it as well.
Right. So what I fixed at Azul was I kept the list of the interfaces, and I did the union type, which was really the worst case, bound on the interfaces implementations. As you went to the runtime, you asked, who implements this interface? You got a list of classes back, and you just superset them all, whatever.
Well, there are two different problems here. One problem is how do we represent interfaces, and yeah, one of the ways is to have sets of classes or sets of interfaces, and you can.
It wasn't sets of classes; it was sets of interfaces.
Okay, but another problem, the one I was talking about, is where do you get these base facts to start with? And
you went to the runtime and you asked, who implements this interface?
But no, I'm talking about the case. Well, let's say you have a simple method. You have an argument which is declarative interface type.
Right.
But my statement is, in runtime, you cannot trust that the object you get will actually implement this interface. So you cannot use this type.
No, right. So that one was done by just doing an interface check at the start of the code. If you went through, there was a thing. Yes, there was a stupid thing you did. You demanded it was the correct guy, and I want to swear the bytecodes had that check in it, but maybe they didn't. But I remember what you're talking about. I just put a check at the start.
So the funny thing is, for classes, we can trust the type because the verifier will check it and will reject anything which mismatches. But for interfaces, there is this clause in the spec which says, well, during verification, we'll coarsen any interface type to Java-lang object. And this is specifically because the type system of the verifier is not adequate to represent needs of different interface types. Yeah. So now verifier will blindly treat any interface type as Java-lang object, so you cannot trust static type information, and you have to do these checks in runtime.
Yeah, but my theory there was the one check at the start was inexpensive because it was covered the whole method. And then at that point, I knew you had this interface at least, which puts you at some point in the class hierarchy. That's the basic.
But then you have to do the same. Basically, for any source where you have where you have interface, let's say you read from a field, you also need to do the same. Or you need to do some kind of check on the store to maintain the invariant that every interface type reference in the heap is actually.
No, I certainly didn't do that. There was an uplifting if I didn't believe you that you had to have, but only if I cared for. Like you asked semantically, you threw it in the C2, and then the C2 just like doesn't care. I mean, he optimizes on it. So if no one uses this value in any interesting way, that check just disappears. So if you're just copying a value from A to B, I believe the check would go away. So this is the C2 at Azul now. The interfaces, I kept the correct semantics, passes all the TCKs, yada, yada, yada. There's all the stupid evil tests there. And it was lifting at the point where it showed up to an interface. And typically I could optimize that away to down to no interesting cost. This let me get through optimize a bunch of places that involved interfaces. I had a lot of potholes that I cleaned up by doing this piece of code, and it definitely passed. So I'm going to guess, I haven't looked at the code in a decade, that it lifted up at every point that you got a raw interface to begin with, and then you optimized, and they typically optimized away. Right, if you don't actually use the value in an interface call to another place, I don't care what type it was. Like if I pull up a thing, it has to be an interface, but all I do is pass as an argument to somebody else who takes it as an interface. I don't have to do anything to it, right? I'm just going to ignore it or ignore its type. And in fact, I believe I lifted it to an interface with a test that then optimizer says, no one cares for this lifted type. I'm going to toss it.
Yeah, and by the spec, you just have to do the check on use sites which use the interface property, specifically invoke interface. You have to have the type check before, and so this is one of the limitations on why it's hard to optimize interface types. Well, you have less sources of interface type information you can trust.
Yeah.
Yeah, the thing I was specifically talking about was where we had in the IR, we had a concrete implementation type. And then there was an implicit conversion to an interface, which was a super type of that concrete type. And the concrete type just being discarded.
Right. And I'm claiming I got rid of that behavior at Azul. So I redid the memory aliasing at Azul C2 because I didn't like how it was done at Sun. Part of that job was to the type hierarchy only had concrete classes, and then you had to the side a list of interfaces you knew about, and that prevented the whole you got an interface and you casted it left or right and lifted it or whatever. If you did something with an interface, I added or removed to my list of known interfaces, but you always had a concrete type that was reasonably precise.
Yeah, I think Roland from Red Hat had a very old patch I recently looked at that did something similar. He just asked the runtime, what are the interfaces for this class?
Right.
You can get it like that. So no interfaces in the type lattice, or doesn't that work with multiple?
In the C2 that I left at Oracle, you could have an interface in the type lattice, but it was treated parallel to capital O object, basically. You were no better or no worse than essentially capital O object. Okay. As you point out, it just stripped all the real type info out. The one I did at Azul, I kept the hierarchy in the lattice as an actual hierarchy for concrete classes, and then I had a list of interfaces. And I just made the list complete. Like if you had super interfaces that you were implementing or subs or whatever direction it went, I just listed them all, because that number of times I cared to inspect the list was very tiny. Somebody does an interface call, I go ask the question, are you of this interface? And I walk the list and get a yes or no in the optimizer, fine. But I didn't, that list was otherwise just carried along as dumb info usually.
Yeah, so attached to each concrete type, you had a list of interfaces.
Yeah, each concrete type that was each concrete type. But it's concrete types that were of the memory pointer type.
Yeah.
The other piece in the memory pointer type was then the root, and whether or not you were precise at the root or you took the subtree.
Yeah, exactly. And there's not null right now as well.
There's a not null property as well. That's right.
And there's a constant property as well. I'm not sure what that is.
Constant, well, if you have a constant pointer to a string, for instance, a reified intern string.
Of course. That's also
it's in parallel with null. It's another constant value. Like there's a set of constants I could have. Well, one of them is your known hard pointer to a hard unique value. Another one's null.
Yeah, of course.
Many other choices there. In theory, you could be a golden object of a class that implemented that, did one exact new at the start of the world, never made another object. You could be the golden instance.
So the Azul JDK, they have two JDKs, right? One open JDK based and one in proprietary, I suppose then. So I'm wondering, can I go look at this patch you did?
So it's a question for Arthur. Well, sorry, go ahead, Arthur.
So you can easily get the binaries. As of getting the code, I don't know.
Okay.
Yeah, Azul is open to acquisition. Yeah.
It's one of the reasons I'm doing so well this year. I gave up on getting money out of Azul, but I did just earlier this year. We gave Oracle that patch. I don't know what happened to it at that point. Like we made a valiant effort to get everything we could into upstream in the Oracle. And, we got a big yawn not invented here, but we gave them code that included that patch. But I don't know what the story, I don't know the story now.
Okay.
But also keep in mind that for the last few, 4 or 5 years, we are not investing in C2 and we're working on OBM compiler.
Yeah. So which goes both ways. It could be that, the new owners don't care. If you tell the new owners, we don't care, this is dead code, they might not care, and then you could let it go. But it probably sounds like work for the compiler team at Azul to go free it out. You get new owners, they're going to be picky. The old guy probably say, yeah, whatever. Scott Sellers, is he still there? Scott Sellers still there?
Yep.
Yeah. Well, you could float it out, make a nice polite request. Run it by whoever. He'll probably tell you to go to the lawyers because some of the stuff was already, as you pointed out, was already given out and just handing out. Oh, actually, you should go to Guild 10A.
Yep.
The correct answer is to go to Guild 10A, and he'll take a straight up email, and I can get you that email address if you want it here.
Yeah, I'll have to ask here as well, maybe to dodge any potential politics.
Well, no, it'd be free to ask for you because you're not asking on behalf of whoever you work for. You ask on behalf of yourself. And if it's open source, be like, whatever, you know, okay, here you go. If you're going to go make money off of it, then you have to go look at the license on the open source patch, which I thought was a reasonable license. That was.
Wait, could we take a quick break to have trolls say something evil while petting the cat? No. You have to say something like, "And I should kill them all," yeah, something.
Some good Bond villain reference.
Yes.
It's a white cat. He's even got a little.
It's actually even worse. This cat has a criminal background. He was brought in by the police. As far as I'm concerned, he's in a witness protection program.
Excellent.
So no tweeting about that cat then. We don't want to dox him.
You know me much too well. I would never ever mention a cat in the tweet. Nice. Okay, there you go. I don't know what we were talking about. So you got a dog in your background. Mark had a dog behind his. No, somebody else had a dog.
That's actually a kitty.
A kitty?
She doesn't know she's a dog.
Oh, okay. I see.
My cat is afraid to come upstairs, unfortunately.
Wow. Excellent. No,
she used to, but I think she fell down the stairs at some point, and now she's afraid to go up.
She's a cat. She fell down and like, okay, fine.
Yeah, well, it's just plain painted wood, so there's nothing really for a cat to grab onto. She starts sliding, so that might be the scary part.
Yeah.
Maybe drank a little too much.
Yeah.
Catnip. Yeah, my cats got used to the hardwood floor, but they didn't like it at first because it was slippery. Then at some point they figured out that when they got the zoomies that they could, you know, pedal as fast as they could, and you'd hear them skating and skittering and sliding around. It was all good fun, but we didn't have stairs to fall down, so that's a fair one. All right, Gil Tenney, let me throw his email into. I don't think if you don't have it. And of course, I don't have it in because God damn it, I didn't get my address book synced.
He prefers if you just call him on his cell phone.
Well, I can do that too.
I'm joking.
I know, but here we go. Here is, well, it's being really slow. Fine. Oh, this is stupid. I forgot how easy it was. Go back to Zoom, go back to chat. Try that one. That's not the only one he has, but this is probably the relevant one.
Matt's slow on the links today, or he should have just already posted the link to the entire, PDF of the contact directory at Azul.
Well, there you go. Matt, if you're like after it, see if you can find anything about that source code dump we did a long time ago. But probably not. I bet you it died without a trace, damn it. Fine. Yeah, Jorn, it was a big, nitpicky, detailed thing throughout C2 because it touched everything to do with memory pointers and aliasing. So there was a large, complicated, excessively detailed thing, plus all the little surrounding nitpicks to make all the JCKs, TCKs all pass. So there's a lot of, like, I wouldn't want to have to replicate that in short order. That was several months worth of work. In exchange for cleaning out a few random potholes, that was the suck thing about it. Of course, it wasn't a huge win. It fixed a few potholes like the one that you fell into, but it wasn't a giant thing.
Yeah, the way we fix it right now is just turn the interface into an abstract class, which was a possibility for us, and that fixes the performance.
Right. You actually hacked your source code. You didn't. This is not a C2 hack.
No. This is Java source code hack.
Yeah. So other people fall in the same pothole. Eventually, you want to do something about it, but it's a bigger hack than it ought to have been. Had I done it right in the start, I listened to somebody else who convinced me to do this thing because it was easy and simpler. Long way to go.
So you learned your lesson. You'll never listen to anyone.
There are a couple of these things like Gradle. I'll never let Gradle run a project that I manage ever again. Gradle sucked giantly. It was hugely slower. It was buggy. It cost many, probably in cumulative, many days of debugging fails strictly for being Gradle-y stupid, not counting the slowness. And the slowness was a pain in the neck.
Well, we chose Gradle because we got to use Kotlin as a side effect.
That's a harder one. See, I would claim I would use Kotlin, no problem, but I wouldn't use Gradle to manage Kotlin.
Yeah, for some reason, Maven and Gradle kind of come from the same philosophical mindset, which is, you know, that there's some atomic, you know, some atomic structure of all projects, and it breaks down to this little thing that has like 3 operations that's the same across everything, except it only applies to Java. And it only applies to Java in a very, very specific style of development. And it only applies if you use very specific this, that, the other thing. And then everything else is possible just by writing completely custom plugins.
Exactly.
But, you know, you could just do it simpler and write the code yourself, you know, like.
Right. Maybe do the same thing, except be 10 times faster and have no bugs. So I don't, and I get rant on Gradle. You can poke me enough and I'll rant on Gradle, but it's not necessary. That's an old one. All right, something else. What we talk about C2 and interfaces and why we care. Okay, so that goes to Cameron's. I think you've answered this before. What do you do for interface-like behaviors, Cameron, or do you just like say no?
So, well, we largely try to make the language look like Java. So we have interfaces, but we also duck type interfaces. Originally, we duck typed everything, meaning if you implemented the same methods and had the same properties as a class, you could pretend to be the class. Then about 4 years ago, we introduced this concept of emulating. So for classes, you specifically have to say, I emulate that class. And you kind of like you could say, I extend C. In this case, you'd say, I emulate C, which means I'm not a C, but I want to pretend, I want to be used in places. And eventually we actually, even though it's a useful feature, you know, we occasionally do kind of this balance of cost versus benefit. And, you know, the benefit, it was only like 3 use cases we had for it. And the cost was enormous in terms of complexity. And I don't just mean in our code base. We think of the big complexity cost as what is a developer
cost of duck typing or the cost of declaring I'm going to emulate?
This concept of a class emulating another class.
Okay.
And then, so finally, what we did find is that duck typing is very useful for interfaces. It's not, and again, don't take this as like gospel.
Yeah.
Because every statement is like within a context. Our context is our language, so you kind of have to take the totality of it. But for our design, duck typing made sense for interfaces. It didn't make sense for classes. So if you implement the same API as a class, you can pass that your object as, the same set of methods and properties as an interface. You can pass an object as if it were that interface, so you don't have to explicitly declare it. There are relatively few times where
you declare an interface, and then everyone can duck type to that interface. But if you're not declared an interface, you're a class and subclassing, I assume, but you're not duck typing.
Yeah.
You're nominative unless declared an interface, and then the classes don't declare themselves an interface.
And it turns out that a lot of these things like duck typing in a static language, a statically typed language, the benefit is actually on the other side. And what I mean by that is the person who wrote that class may not have written the interface. So someone comes along, looks at the class, says, I like that design. They take the interface, but they want that class to fulfill the interface without going in and changing the class.
You're trying to put a narrower API on a class that does something useful.
Right. So now they can continue to use that implementation of that class without actually changing, because let's say they don't own the code, right? It's someone else's code.
Yeah.
And so it becomes very useful at the boundary among modules, right? That's where duck typing becomes very useful. Because within a module, like you just add, implements X and you're done, right? Like, no big deal. But it's across modules where you don't. I don't know if you guys can hear my concert oboe player in the background.
Yeah, not bad.
We have, that's my daughter.
Great.
Anyway, but across modules, where you don't own the code and you're not able to change someone else's code, and where it's versioned independently. So maybe they introduce the interface at a later date or something. So you have challenges across those inter-module coupling points, and that's where duck typing becomes valuable.
Yeah, that's very insightful, and I thank you for sharing that.
Well, I didn't understand the benefit of duck typing when I started, right? And so it's like you kind of have to do things wrong, realize that they're wrong, and then sometimes in the midst of that you realize, oh, there is actually something really cool about something useful, valuable to someone about this.
Right. No, finding what is important in any particular decision is finding where it applies that mostly other things don't apply, and you can solve uniquely here. And of course, everything overlaps heavily otherwise. You have to not be in the way. And it's a hard lesson to pick up what's important about these things.
And additionally, you have to think of it kind of like solving an equation in a way, in that each thing you add has to make sense in the whole, right? So it's almost like each feature is a new dimension. So now you're solving for one more dimension, not just one more variable per se, but it just introduces its exponential complexity. Each feature adds to that exponent. So if you add features late, that's because you didn't bake them into the matrix, if you will, early on. Adding them late is inordinately expensive, which is why I almost prefer, design wise, you start with too many features and then you pair them back, because it's much easier to jettison them than it is to add them.
Yeah, well, for the implementer, for the users, they have to go and re-implement if they were using
No, I meant before 1.0, before someone uses it.
Yeah, so I'm kind of in the zone of I wanted to do duck typing, and I have an implementation that regionally duck type. And I'm also staring at subclassing, and I've loved using subclassing in the past, and I was trying to figure out what the cross product is. And what I just heard you say is a useful cross product is subclass unclassing as expected with nominative only typing, declare an interface, and anybody who matches that interface can now make a call as if they are that interface.
Right, so there's either an implicit cast or an explicit cast, but it's something that can be checked at compile time.
Right, so you don't have items of an interface class only. If I want to call through an interface, can I have a pointer to an interface that I'm going to make a call through?
Yes.
Only know it as an interface, because of course it goes to one of a variety of subclasses for which the duck typing fits you on.
So in this case, we actually have, if you remember, our references are not just pointers, they're actually conceptually, they're two pieces of information. So it's a type and a identity, which you can think of as the pointer, right? Yeah. So think of the identity as the pointer to the struct, and the type as the pointer to the vtable and RTTI.
Okay.
So, and most of the time you only have one or the other, you don't have both.
Yeah. So say it again.
So think of what we call a reference as two pieces.
Yeah.
It's got an identity, a type and an identity. So the type is the RTTI information.
Right.
And it's not necessarily the behind the scenes, there is the RTTI information for the object itself, but it's the RTTI information for in this case, the interface. So I can actually have a reference to let's take a Java example, runnable. It's an interface with one method. So I can have a reference to a runnable. And when I'm handed that, I can say, well, what are you? I know it's a runnable. Yeah. Or I can say, what are you? And it'll say, I'm a runnable. And you say, no, I want to know what your class is. And it can say, sorry, I'm not going to tell you. In other words, the only thing you see is that runnable slice.
Okay.
That's what we call masking as. So when we inject something into a container, it's masked. So if we were to inject a runnable, sorry, I don't know if you can see my Italian hand motion. So we inject a runnable into a container. Now maybe it's, some super duper top secret security thing, but instead when it comes into the container, all it is a runnable. You can't cast it to something bigger, even if you know what the implementation is, even if you know what the class is. So that's what I meant by type. So a reference comes with a type and it comes with an identity, which is, if you will, the pointer to the object.
Okay, so, and now that you have a runnable and you want to make a dispatch call against it, and you're limited obviously to the interface, what's the dispatch mechanism?
So the design, because right now our implementation is a proof of concept interpreter, so take that off the table. The design is that we would create for each type where that object is used, we would create a vtable for that type. And this is almost, you're gonna hate this. It's almost COM-like, in that COM, you remember the old Microsoft will export C++ objects and DLLs. Yeah. In that an object can have, in C++, you generally only have one vtable for an object, right? Because we have these two parts of the reference, the handle, if you will, because we have these two parts, we can substitute a different vtable. Yeah. So we don't have to do, so the indirection is in the indirection, if you will, is in the creation of the vtable as opposed to what C2 does. So C2, I guess, has one quick path on an interface, and then it has a lookup or something, right?
This is the interface call, not the creation point.
Right.
Yeah. The interface call mechanism is actually very generic, and you could take it. And there's a paper on it with me and John Rose. And it for Java, it makes most calls one clock cycle, most cast operations one clock cycle, and most interface calls plus one clock over a static call. And the main hack is that you can cache one class, one concrete class of what you love. And typically in Java implementations, that cache never misses. It misses one time going from empty to full, and then never misses again. That's an inline cache. And the cast has a similar behavior in that there is a cache for interface. There's a cache which you test as part of the standard lookup. So knowing some parts of a call, including how deep in the class hierarchy you are, and do you are a concrete class versus an interfaces, and are you known sub with a known super, the optimizer cleans them all out. The usual story is you take the class from the object in question, you compare it to a constant, which is your known goodness, and you cast and you're done. The second story is I loaded from the class hierarchy table, which is kept in with the class metadata, which is one pointer load away, at a fixed offset according to how deep I was in the class hierarchy. And I pulled a constant test and ran. For interfaces, the first test is pointed to the one entry cache. And I look at your concrete class, and if you match on the concrete, then I declared you're that interface, and I run away. Yes, that's the paper, thank you. And if that misses and you're an interface, then you fall into do the linear scan of an array of interfaces that are implemented here. And so people who flop concrete classes at an interface call suck it and do the slow way, which, like, funny new languages on a JVM all fall into this rat hole. You know, the JRubies and Jythons of the world fall into this rat hole. Other things are not doing these other language implementations typically never fall down the interface rat hole. So that's the paper. It explains how to do it. Yeah. So I had a different question. Are you using fat pointers? Are your pointers fit in one machine word?
That's the plan. Yep.
Okay. So you have some overlapping of bits that you're going to steal from left.
That's right. So for example, if I'm passing an int, to something that takes ints and something else, I could mark it as, this is not a, vtable pointer and a struct pointer. separately, I could say this is a, trust me, it's the built-in int implementation of this value. So in other words, conceptually, I still have a vtable to int.
Yeah.
And a pointer to a value. It's just that the value is in the handle itself, and the vtable is fixed.
So if your ints are, the fast version of your ints are less than 64 bits?
They are 64 bits.
So you
But
have to pass 64 bits plus some other token saying I'm an int, not something else.
right.
So I would claim that's a fat pointer. Why is that not a fat pointer?
No, I'd say it's a fat pointer.
Oh, I'm sorry. Okay, I thought you said you were going to fit in one machine word.
Well, I mean, it's a virtual machine, so I don't know what the size of the word is, but yeah, I mean, it's that'll be the game, right? Is how small can you stuff, because we're trying to trade off kind of passing more information in the handle,
right,
without needing 10 times as much space on the stack per function, right? I mean, that's the trade-off.
So Azul pointers carried, the hardware Azul pointers carried the class ID in the pointer.
Mm-hmm.
So, but you limited yourself to, I think we chopped it at like 19 bits or something. You lost a pointer to the GC, you lost a bit to the GC, and you lost somewhere between 16 and 19 bits to the class ID. And then the rest was your heap, which still gave you many terabytes and beyond of heap space.
Was that a 64-bit pointer then?
It's 64-bit pointer, yeah. And the hardware stripped the bits. And I guess we didn't keep that on the X86 version. It did have a useful property that then we could do a class check against the header bits directly. We had a hardware instruction.
Right.
One cycle, are you this class? And that was an inline cache. And subtyping and all those tests didn't have to fetch the first word of the object, which if you're just passing an object around, you have to load in the cache line with the first word because you're just passing it around from left to right. So there was some benefit. You usually ended up, if you're going to do something with it, you got the first cache line anyhow, but there was some help there. Mostly it let us get away with avoiding a load on a dependent test path, which an X86 kind of does super efficiently already. So you just eat the load on an X86 and you don't care.
Yeah, it's kind of a C++ optimization, right?
In the mindset, yeah.
I'm saying the X86 optimization is for that purpose, I think.
Oh, no, it's just because it's super common. I have a pointer, I load a value, I compare it to null or compare it to a constant, and I jump. So load, compare, jump. X86 will do that in essentially one clock cycle, plus or minus branch prediction. As soon as you have an inline cache, prediction rate is 99.99%. So that's definitely a clock cycle only kind of thing. Well, they had to do it because endlessly no registers, so you'll always load, right? And so specifically things in and out of the stack, and specifically things that are load, compare, and branch are super hot on an X86, whereas on a sort of an ARM risky older generation thing, you could imagine you'd have things in registers more often and you didn't need to load constantly. X86, out of registers, loaded constantly.
Yeah, I mean, 4 registers should be enough for everyone.
Don't laugh. The first C2 totally jitted code for the 8 register X86, right? Stack pointer 8U1, you had 7 registers. That was the first C2. We were making benchmark war winning scores on spec JVM 98 on an 8286 machine, right? Whatever, madness.
I'm not going to date myself by saying that we used to use some of the spare flag bits.
Oh yeah. Oh, we went back and forth on that one. So long math to do with add with carry. You had to move the carry bit around. So we tracked the carry bit in the register allocator so that we could, schedule instructions and do things with it. There was one early disaster while I was at Sun involving Paul Hohensee, and I'm going to take your name in vain here, Paul, and you can shoot me if I'm wrong. There was a patch made to do 64-bit math using 64-bit registers, because Spark had 64-bit registers for x86 did. And the patch said, you know, x86 will mimic 64-bit registers on its 7 available registers by pairing. So you had 3 registers paired. And the performance of that was, I don't remember all the details. I remember the performance of it was like totally miserable, because the main consumer of long math at that era was crypto, was big integer, doing crypto. And big integer math all had this behavior where they took 2 ints and squished them as a long effectively. But they did shift left, shift right by 32 all the time. And if you break all those up as the independent parts, the shift left, shift right by 32 stripped down to individual 32-bit integers that you could freely allocate among the 7 registers, which C2 totally went to town on. So flipping to a 3-register model from a 7-register model was like completely miserable for x86, even as it helped Spark. So there was a reject on that push, and followed by sort of a panic effort to do it right for both, you know, both machines, followed by, within a couple of years, Intel finally having a 64-bit platform that was widely available and we could quit coding.
Well, AMD. I don't remember working on what you described, but I did do the AMD port.
Yeah, AMD would beat Intel on this one. That was a big deal. Nice seeing you, Ludovic, Henry? Guy with 2 first names. Not the only guy I know with 2 first names. It's all good. Yeah, that was, you know, there was some history there. The whole 64-bit math disaster, that was a fun one. That's on one of my slides. I talk about, well, I'll never do again doing 64-bit math that way. Yeah, it's all water under the bridge now. So you're thinking you're going to not have fat pointers. You're carrying type info in the pointer itself, including, because you're going to do ints, you're going to do.
I'd call that fat pointer.
Yeah, if you had to pass what is conceptually a single scalar value in 2 or more registers, I claim you're fat.
I see. So you're using fat vis-a-vis the machine word size.
Yes, because it goes straight to the performance implementation. There's a lot of performance impacts. Like if I didn't care about fat, I can make, you know, fat pointers be gigabytes in size, and I'd just pass the gigabyte and copy it everywhere, and it's just gigabytes I'm copying. Okay, that gets expensive fast. Okay, so maybe I don't copy gig. Kilobytes, maybe. You know, tens of bytes. Okay, that's still kind of expensive. Okay, how about 128 versus 64? Is that expensive?
Well, the other thing is, if you're generating the code, you're not necessarily following an ABI that, you know, an interoperable ABI with another language.
No.
So your options are a lot wider.
Yes.
Than just
things. Yeah, I did a job that was completely separate the APIs from, you know, Java to native, Java to the VM, which was C code that we had control over, and native, which was the classic x86 ABI, versus Java to Java. Absolutely, and totally worth it to go there.
You know, so for example, if I need 66 bits, I can just pretend that a word is 66 bits. And then, you know, in my calling convention, I only need, let's say I'm assuming 64-bit registers, you know, up to 32 parameters. It uses 1 additional word on the stack for.
Yeah, you threw some extra bits somewhere. You didn't care where you go. The register allocator's job is to sort where they landed in the stack or a register. That was the other thing I did with the register allocator C2. You just, all stack was another register, just more expensive. And he sorted the registers however he wanted to, including stack. So he made very dense, well stack colored the stack as well as registers with the same coloring mechanism, same cost.
I guess what I'm saying is, like, you know, without being, if you're not forced to use an existing ABI, you can have, you know, 66-bit words, for example.
The extra bits don't cost as much.
Right.
Yes. They still cost you. So here's the cat.
Yes.
Open the door. He's like, nope. he He aborted. Still too cold. Come here, you. Yeah. There he is. Okay.
He's a
like
pretty
right
kitty.
away from the camera. He's like 17 or 18 or something. We're kind of sort of know his age because we inherited him, but he's a super nice cat. Mostly super needy. He's like a dog. He'll come when he's called. You got a dog like a cat? I got a cat like a dog. Yes. Fine.
Wait, these AMX instructions, is that just a machine learning hack for doing dot products?
Well,
We'll be stuck with this forever, won't we?
Intel will claim they're doing matrix math, and whether you do
Yeah.
that for machine learning or do it for graphics or anything else, it's up to you. Certainly smells like
you do it for benchmarks because AMD hasn't implemented AVX 512 yet. So every benchmark has to be AVX 512 so that Intel still has an advantage.
Yes.
But the registers are useful.
Yeah.
No, but AMX uses a different set of, doesn't
As far as I know,
Yeah.
it's new.
a new 2D register file
Yeah.
and some new register. I mean, this looks like a different thing. So yet another vector instruction. Well, it's not really vector instruction set. It's even more specialized than the vector instruction says. This can do one thing, and it can do the inner loop of a convolution of 16-bit floats.
Yeah, I was gonna say it smelled a lot like a deep learning neural network.
But we'll be stuck with this forever, right? I mean, this is implemented in Sapphire Rapids.
At first, I'm hearing about it, but that's the typical answer. Now, having said that, they have in the past done things where they take hardware interrupts on. They have subclass X86s that take a hardware interrupt if you use the instruction and jump to an OS software implementation, right? It's not such a thing necessarily. And the JVM asks that damn CPU ID question, and I know it emits different instructions and contexts according to what your hardware actually has.
Right. I'm not opposed to adding new instructions. I like the various vector instruction sets, but this one is too specialized. I mean, it has 8 instructions, and most of them have bookkeeping, and it has 2 instructions that actually do work.
It looks like a chunk of it's a convolution. Okay, matrix multiply. That seems fairly. I'm sorry, it's a dot product. Yeah. Isn't that fairly useful?
16-bit floats is useful
for
one thing.
16-bit floats. Oh, there you go. Oh, that's machine learning only. You're right. That's
it's ML. And are they IEEE 754 32-bit floats as 16?
No, they are brain floating points.
Yeah, that's a 32-bit float.
Where do you see I see the cut
B float 16 is an IEEE 754 32-bit float with half the bits missing. So you just cut off the half the bits and throw them away.
Wait, 32 bits cut off half.
Because you don't need the precision, you need the scale. For ML, you don't need high precision floating point.
You're literally throwing 30 because there are 16-bit floating point formats floating around that do hell a lot better than just drop the last 16 bits of.
If you were so smart, you'd work at Google and throw away 16 bits.
No, so the idea is that with this, you can kind of have factor out the precision and have some precision bits that cover many B16, right? So this does make sense.
So like I said, bfloat 32 is literally IEEE 754 32-bit minus 16 bits. And it's literally half. They chop it in half and throw half away.
Well, when you say half, you meant only mantissa bits.
Yes.
No exponent bits.
Right. You only cut off the mantissa, so you have a 7-bit mantissa instead of 23-bit mantissa.
Wow. Like I said, I worked with a guy doing a startup. He was trying to do a startup. He was a smart guy, but he had a better cut precision math in a lot of ways than even IEEE 754 spec. But he could cut arbitrarily bit sizes, whatever size you wanted, and he had a software library implemented.
I'm not saying this is a bad format. It makes a lot of sense, and I think it's a good idea to try to innovate on floating point. It's as an instruction set. I just think it's dubious in a general purpose processor.
Yeah. Yeah, there you go. Just whacked it off. Although float 16 cuts mantissa bits. Cut 3 bits from mantissa. Float 32 looks like standard IEEE.
Yeah, but you don't. That's you don't have that float 32 in the instruction set. That's
oh. Well, float 16 cut 3 bits of mantissa. Oh, and B float 16 did not.
It preserves the exponent in order to preserve the range, but it cuts the significand in order to reduce the bits used for fraction.
Right,
Correct.
right. For TPUs, yeah, here it is. There's their TPU discussion. For TPUs, for deep learning, this makes sense. Because what you lose in one weight, you can gain by other weights. But the learning will pick up elsewhere. Wow. Okay, fine. Fine. Learn something new every day. Yeah, that discussion's been around a while. I guess that's how long it takes Intel to come up with the hardware, actually. I wonder if, do they say Google go pay Intel to go make chips for them? That would make sense.
So I guess currently they just load one of these things, extend it to 32 bits, do the math, and then truncate again. Because they are in use already, right? Half floats.
Well, half float's been around. Concepts, like I said, concepts been around a while. Whether or not TPUs do this, or Intel or Google doing it for their thing. Certainly, a software-only version of deep learning I did for H2O did 64-bit math. But we would chop to 32-bit precision if you asked for it, because the half-size model meant it was cheaper to keep you fit in your freaking L1. You wanted the model to fit in your L1. This was not GPU based. This is X86 compute. So we had a 32 and a 64-bit version. Yeah, fine. So B, yeah, as in Neoverse. Okay. Wow. Yeah, it's like the New World Order. It's just like custom math. I still remember the era when people were arguing pre-IEEE 754, arguing over math for precision versus errors versus not, or whatever. Here we've said, okay, we can agree that we don't care. We're going to throw these bits away. Honestly, there's probably a lot of jobs in hard real time for control systems where you desperately want to know about overflow and underflow, but you don't need that many precision because your damn A to D, D to A converters are only 8 bits anyhow. Java tools, constant B, what?
So the second link, I messed up with the first one. The second link, it basically shows how you take a Java 32-bit float and create a bfloat 16 from it.
Oh, you have code for this already?
Yeah, we support bfloat 16. and we support matrices. And I may or may not have asked Intel to add support. But I'm sure I was not the first.
Okay, yeah, good. Go ask. We tried to get Intel to do stuff for read barriers for Azul GC, and they were less impressed. So the GC did read barrier on software and still pays a cost. And I don't know, Azul's still in business, so.
It's always random what they decide to add.
Well, as Joel points out, they have to support it forever. So I get their reticence. Sorry, Joel.
Is actually supposed to be for machine learning? I mean, what do you expect your users to use bfloat 16s for?
Yes, for machine learning, yeah.
Really? I was thinking you were doing generic cloud web scale things, but not ML.
Well, ML's part of that.
Yeah, it's one of the use cases. You target ML specifically, you make some different design choices though.
But also the number crunching parts?
Yeah, that's what I'm saying, the number crunching parts. I made very different design choices, and Exchange got fairly dramatic speed ups around the number crunching.
Yeah, I would argue that ML workloads are becoming more and more
they're common, yeah.
General purpose, yeah.
Oh, and no, you're saying general purpose.
No, I'm saying it's becoming part of general purpose workload. I mean,
yeah, it's an exciting workload. There's a lot of folks doing it who pay money. They want to know better. Yes, I totally understand a business case there. If your goal is to pound out terabyte-sized matrices and do math on them as fast as you can, there are some design choices to be made that are kind of orthogonal to a lot of what you do, but I know about what you do, that we could have a conversation on.
The idea in general is most of the heavy lifting will be done in libraries, but to work with those libraries efficiently, you want to have a type system that respects the requirements of those libraries.
Okay.
So
I was implementing those libraries, and we had a lot of call from people who wanted to work tighter to the library than calling it itself, because they wanted a core algorithm that was up and running, but then they wanted to fine tune it. Every data science / mathematician who knows some amount of something would be very happy to start with a well-functioning, say, generalized linear modeling algorithm, which is a big, hairy, complicated tarball, even if the math is straightforward and simple. And because the math is straightforward and simple, they're going to come in and add any number of bazillion things that are crucial to their particular case that we ended up doing at H2O eventually, but we hand managed the library. There were a lot of folks who wanted to interface tighter into every possible ML algorithm. So I'm just saying, if you expect to draw the line at a library, expect to hear some yelling and screaming, but I want to cross that boundary. And if you throw up your hands and say, yeah, well, now you're writing bare C code, people be not pleased. They want to play with these things. We had a lot of that discussion, and we had some people who dove under the hood and went in at the H2O/Java layer and hacked on the algorithms directly.
No, it's terribly, terribly challenging to provide both a brilliantly good abstraction to a technical user and get the last clock cycle of benefit from a performance standpoint. Those two things tend to be in contradiction.
We got the last clock cycle out, and it was kind of challenging. I tried hard to make it less challenging, and I claim I did a reasonable job, but it was not so straightforward. The API that you coded to, I thought was pretty reasonable, but it wasn't. It wasn't Python-esque. You had to understand that your data was distributed. You had to understand whatever. We go down there if you want. That's a different story. It's how you write a big data abstraction library that's functionally useful when data will span multiple nodes. Cannot be held on one node. It physically will not fit. So you must code distributed. So you have to limit what you do to what goes distributed.
Yeah, and it's kind of distributed in three different ways as well. I mean, you're talking distributed on a network, but typically within the machine, you're also distributing between, read-write memory that the application is using, and the same memory is also read-write by the PCI bus if you're accelerating it on, on a Turing card or something like that. So
we have to fragment the memory on a node so you get multiple cores.
Well, there's that, but I can also use
GPU.
Yeah, eight GPUs, and
so
each with 4,000 cores. I mean, it's a completely different game.
So if you're doing neural nets, GPUs win. If you're not doing neural nets, and not every problem is well solved with neural nets, touching a GPU is generally death, because the cost to get it on and off the GPU exceeds the algorithm.
And that cost is also diminishing rapidly. And so you see that with this unified memory architecture, for example.
I haven't tracked that cost. 5 years ago, if you didn't have 1,001 compute to bandwidth ratio, touching GPU was death. And a classic GLM would have almost a 1-to-1 ratio of compute to data.
Well, and I gave you the two distributed concepts of network and then between the CPU and your accelerators. But the third one is the killer, which is what you're touching on now, which is the callback. In other words, you know, deep inside this highly accelerated process, I want you to call this particular discriminator or this particular calculator function. And this is where, you know, if
okay, I would say our API was, it was not deep inside, or you wrote Java code deep inside.
Right, but I'm saying if you have 4,000 cores on a GPU and you stick 8 of them in a you know, in a rack server, so you've got 32,000 cores,
yeah,
crunching this, and then the callback is implemented such that the CPU has to run that code because of the language constraint. Then,
well, because it's complicated and difficult, and a GPU would be horribly slower.
Right. What I'm saying though is that you have a mismatch.
Yeah.
That's a serious impedance mismatch, and it just the wheels just come off completely. So that's another challenge for this type of.
Right. We decided that we would bottom out a GPU specifically for deep learning, and implement on the only a small set of functions that you put in the core that people have choices over. What the hell the names for them are, but the weighting functions. Everything else, we didn't touch GPUs at that time. This is 5 years ago, because the cost to get to GPU was way too expensive compared to the compute cost. So like you do a random forest, GPU will just say it nasty, but will not do well on a random. I don't believe a GPU as of a few years ago would touch a random forest for computation. Just totally the wrong set of math for GPU. Extremely irregular all the way down the line. And diminishing tiny data sets that have to be managed, whatever, fine. So, you know, random forest was on the X86, and you wrote Java code in the core inner loop to do random forest. Same for GBM, same for GLM, but that was because you didn't have a huge amount of compute. Now, GLM also had a damn ass big matrix multiply, which anybody doing a good job with faster matrix multiply, we could go back and forth.
Right. So that's the GPU cases tend to be with pretty large vectors and pretty large matrices. Yep.
Yeah. So yeah, the like GLM, the numbers are row count, which is n, and row and column width, which we call p. It's n times p squared, where p squared then, if it's under 100, is a millisecond or less, and n is scalable across all cores and is 1 nano. And then plus a p cubed number, which is between passes. So 5 passes, 6 passes, p squared n plus p cubed, usually n dominated. But if you got a big enough p, you'd have a big matrix multiply, and that one you wanted to throw on something else.
Yeah, I'm not a practitioner, so 3/4 of what you just said went right over my head. I don't mind admitting that, by the way.
Here, let me see if I can put it in the chat. So the cost function was this, where, you know, in equals rows. Roughly, maybe more like something like that, more or less. I don't probably have p right yet by an order of magnitude or two. Like p cubed at 1,000 was becoming an hour, and 10,000 would hit a year on an x86. And at 100 was under a second, we didn't care, it was a millisecond. Where n was terabytes, but divided by CPU count. Typically actually capped by memory bandwidth across your cluster. So that's a GLM. That's a generalized linear modeling. It's a very old, but still very useful machine learning, because it's fast and because the model is entirely interpretable. Everyone should do, if they're doing some sort of data science project from the start, as soon as you have a clean enough data set, you should run a GLM for you anything else, because it's stupidly fast and you understand what it does. And it'll tell you all kinds of stupid, easy things like, all these columns are junk and mean nothing. And also they're all collinear anyhow. And these columns tell you the 99% answer, and you have 3 factors that matter, everything else is trash, and you're done, you walk away, and that's the end of the problem. Yeah, that's the kind of stupid thing they do. Or they come back and say, Yeah, we got kind of a gross, ugly fit, and it uses every possible term in a small linear sliding scale down to the low end bits, and GLM's not doing a good job here. So it's an easy, quick way to like touch things, and the only issue is you have to decide if you are fat or tall. And we were all geared for extremely efficiently tall, skinny data sets, and there are people who did, you know, fat. And you want a different algorithm, and you have different constant factors. Fine. But this one would do terabytes in seconds without any trouble. That was a good thing. I mean, it was entirely useful. So I'm just trying to figure out if ignoring the GPU, which is not a safe thing to do, obviously, ignoring the GPU issue. What you do in a hot inner loop over large data sets can matter by you know, every one of these constant factors. If you said double the in cost, that would be unacceptable very rapidly. So it's useful to bring that cost down to the minimal count.
Yeah, and generally the GPU is when you want to eliminate the loop altogether. So
the GPU, you want to not shuffle data back and forth, because there's a cost to do something. Like the GPU cost will take the P count divided by 4,000. You'll still be P cubed, but you'll divide it by 4,000, right? Per GPU. So it's a huge division factor, right? You put a rack together and you've got 64,000 dividing by, okay, that's pretty exciting. It's still P cubed, but it's divided by 64,000 is big. Okay. But plus, I'm going to add the cost to shuffle a terabyte onto a GPU. What's that time? Well, okay, so at some point, those factors, you do the math, and at some point don't make no sense to touch the GPU. If you drive the cost to get to the GPU down to 100 to 1, then it changes where you do which piece of the math. You start back and forth.
And I haven't used, you know, any of the CUDA or any of those directly, so I'm, you know, most of my knowledge is from reading white papers at this point.
Right. I only started this path and then I walked away from H2O, but I know it got finished when after I was out, but at the deep learning layer. And there were a bunch of people doing Java on GPU for deep learning, DL for J, deep learning for Java. What was it? There were like 3 of them in a row, all same concept.
Yeah, and
PyTorch.
the Sun Labs, well, Oracle Labs was working on it a couple years back, but I think they largely moved on from that project. Guy Steele was working on that project.
Oh, Fortress? I'm talking
Detroit,
Fortress.
I think.
Post Fortress.
Post
Project Detroit.
Detroit. I don't know that one.
I haven't heard the name before.
David Bacon was working on a thing he called Lime, which was about doing Java to GPU conversion. I don't know if that's not inherited anything from Detroit. That would have been from the same labs.
There's also a Tornado VM. I'm not sure. I think it was a PhD that wrote a Gradle VM plugin to do inner loops on, or to do any loops on GPU, FPGA, and CPU on different cores as well.
Sure.
I think there's a pretty good talk about that as well.
I think one of the overlying themes here is that we still don't have a reasonably programmatic cost model to let us know when to shuffle these kind of algorithms left or right, like in a generic way. Like in the case of GLM, I can switch to a stochastic algorithm if I know that you're very wide, very shallow. It's common in like medical and natural language processing. But I do that because I know the cost of 2 different techniques, and I do an if test at the beginning, and I says you are n times p is greater than blah, less than blah, do this, do that. But that's not a generic way to go about it. Hey, I got a 1,001 cost model to do this. You know, I add a
so
second.
how would you hotspot it, I guess, is the question. Right?
I think the interesting thing they did for the Tornado VM is that they would just try it out. What if you run on the CPU? What if you run on the FPGA? And what if you run on the GPU? And then pick the best one out of them dynamically at runtime. I'm not sure if they did any caching as well, but that was the basic idea, I think.
So they did it both ways, and then like aborted somebody who was losing, I guess, and kept the winner. The winner got first, and the loser got aborted.
Yeah, exactly.
That's interesting. That's actually kind of hotspotty there. No, I was looking for any sort of formal approach where you could go ask the question ahead of time.
Yeah, but that's like solving the halting problem, right?
Maybe. It just seems plausible to me that portions of it should be solvable without falling off the pitfalls of the universe. Like I could claim this is halting, yes, over here, but as soon as I hit a GLM, that's not halting. Oh, it's distributed. So there's network calls, there's parallelism, there's concurrency, there's huge array math things, there's compression, decompressions. It's big, hairy, complicated. It's going to halt. And it's going to halt in the numbers I gave you. So why can't I have any sort of reasonable language annotations that come along that says, this program, in fact, halts in order, and here's the params that dictate the big O notation. And I don't have any way to say that in a language and pass that information around and do, compiler side educated guesses. If you were to make this change to your program, it goes from halting shortly to being, exponential. And by the way, you just wrote an exponential algorithm. Do you care? Be nice. I don't know. Fine.
Well, you see, I mean, you're kind of asking what's the costing model that the optimizer can use when analyzing the code?
What's the costing model a programmer can use when they're trying to understand the algorithm they're writing? Right? Yes, if I can get it down to where an optimizer can do it, then a programmer can do it too. I'm asking a question, is there a way to add some sort of compiler typing language annotation, wherever it is, that tries to help you understand cost? Here's a simpler model. Let's suppose I want a typing annotation that lets me know that this thread will block. So I'm trying to do a reactive GUI. I just want to know blocks or not. That's the only question I have. Is there a way I can type it? Well, if I bottom out at any of the following OS calls at any point, then I want to claim, yes, you block because read and write block. So feed that up the typing chain. I have a set of calls that will block. I have a set of calls that will complete in some unknown amount of time, but they'll keep running. So presumably they'll get to an end. I didn't get the big O notation. It could still be, solving heat death of the universe. I don't care, but at least they weren't blocking. What is this? Resource, ML. Yeah, resource aware would be, I have to go turn it on. I'll stare at this. And then I'm looking for static analysis side, but I guess you could have a dynamic one. Like I really wanted to, so many times I wanted to know, I'm trying to write a fancy web GUI for a mobile device. Is this function call going to block? Because if it's going to block, I have to make a callback for the blocking point and pass that up and down because it's JavaScript, pyramid of death blocking strategies, or switch over to the React version or whatever you're going to do. Append 1 to match. This is like walk down. Oh, I don't know what this is doing. Whatever ML tick does. What's it do?
Did you see the next link on the static analysis?
No, I hadn't get there.
If you click the play button, if you're still on the RAML, it can infer the polynomial, which gives you the bound. So for example, for the first example that you are going to load, you are going to see something like inferred simplified bound 3 plus 11 times m, where m is the number of cons nodes. So there is basically an example that conses something onto a list, which is appending the elements. And it can infer that this example is linear in the
that's what
number
I'm
of the elements.
Right. Yes, this would be awesome if it were even if it bailed out fairly conservatively fairly often. There are plenty of times what I would love.
In general you have to, because it's undecidable problem, but you can do some conservative.
Right. I would love to add a type annotation that says it is a compiler error if the compiler cannot prove this is linear in the input. If the compiler can't prove it's linear in the input, blow an error at me and I'll go stare at it.
For termination specifically, you often have approach in so-called total languages when you provide fuel. It's essentially just like the fuel in compiler testing when you want to bound the number of steps. So that's fairly common.
Yeah, I've been talking to the Tezos guys just earlier this week about gas.
I remember this from the Galena language in the Koch interactive theorem prover. But I think that's fairly common.
They were using Koch as well. Yeah, I would love to have a language annotation that did something along the bounds of this runs in time big O of input, or big O squared, or polynomial, or dies, or the compiler can't prove it. And if the compiler can't prove it, that's exciting as well. Just to keep me from accidentally writing n-squared algorithms when I swear I'm writing a linear one. Happens all the time. Yeah, okay, so this analysis tool claims that he can annotate or do something and then blow up and show you that you've changed your analysis costs to something much more. That's interesting. Okay. Yeah, infinite execution time. Yeah, okay. Huh. Wild. See, now I want to go play. Java. All right. Well, that's interesting. Okay, so this is, learn something new every time. So progress has been made on this. This stuff's been around for a while, but progress has been made. Actually, the resource-aware checker, that guy, is he actually run this code and like looks at it? He claims he's type checking. Trying degree 2. So I need a more complicated example. He probably has one. A bunch of them. 99 problems in OCaml. I guess I'm staring at OCaml these days. Ooh, he's got some interesting stuff. Wow. Okay, we have to hit the button, see what he does. All right. I'm playing with the toy now instead of moderating a conversation. So the first thing that happens is he's slow. There you go. He did complete, and he claims, wow. He claims bounds that are pretty tight. Holy crap. Okay, this is like doing something interesting.
I can see you're going to have a long weekend.
All right, Kat. Now I'm going to push you. There you go. Yeah. Okay, fine. I put it down. Yes. Simplified bound. Boom. Yeah, he did some 1,000 lines of OCaml code in 30 seconds or a minute and came back with an interesting answer.
Also, looking at the publications, I linked some. They also link on the website. It's kind of interesting because they say they basically do amortized cost analysis. So if you remember, that's the same amortized analysis that you have in ordinary algorithms textbook. Like, say you have this geometric growth strategy for dynamic arrays.
Yeah.
And you can show that this one is amortized constant size for the pushback. So that's the same, pretty much the same kind of analysis they are doing.
Wow.
Pretty amazing how far they are able to take it. I think it's pretty cool.
Oh. Cool. Okay.
I think I saw one of those talks, by the way.
Online?
Yeah, the conference was online.
Sigplan.org. All right. I'll quit looking at them.
So funny enough, there are a couple even smaller than bfloat 16 floating point types being used, but none of them has really caught on yet. There was even, I want to say it was like a 2-bit floating point or something that someone used for some extreme. Yeah, I mean, as with any good idea, you can take it far beyond its logical conclusion.
Caveman counting. 0, 1, 2, many.
Well, right. It's 0, small.
Yeah.
0, tiny, small, and infinite.
Yes.
Or some.
Yeah. Something like caveman counting. Well, caveman's a little more precise. It ends at 3. He runs out of fingers. Yeah. I would love to hear the use case, but it probably don't make any sense. It's all good. All right, another one. Matt's on a bound again, on a roll.
I think it's with extremely large matrices. So let's say you had,
yeah.
Let's say you had to stick it inside a single computer's memory. You know, you max out at around 32 terabytes in a computer. You know, so if you can drop it from, say, a 32-bit float down to 2-bit float, you know, your matrix size goes up by 16, and your precision isn't the important thing. And that's what they learned with bfloat 16. So Google actually did some, I think it was Google that published the papers on it, where they did some analysis of how much precision the ML lost, the ML result lost based on using 16-bit versus 32. And they looked at it from two different perspectives. So again, keep in mind, I'm not a practitioner, so I'm just repeating things that I read online. But they looked at it as you know, with the same size matrix, how much did you lose? But then if you could double the size of the matrix, how much?
Yeah.
And it was dramatically better, and that's why they ended up settling on it as a data type.
Oh, interesting. Okay.
So it's not just that they could get. It's not just that it was smaller, faster, because it's probably not faster.
Double weights counted more than half weights, double precision. Yeah.
Right.
You double the count of weights in the matrix. Yeah, this is a deep learning specific solution, which is fine. I'm curious to know if that applies to other things.
I haven't seen any use case for bfloat 16 outside of ML specifically.
Yeah. Oh, out of ML specifically, I can imagine it would work well for random forest. It might not work well for GBM because of how GBM works, but it might work well for random forest. And GLM, you'd only care about the p cubed part for performance on the matrix to solve it faster.
So Matt, any recollection of the paper I was talking about where they were comparing the benefits of the bfloat 16? Because I think it's a pretty well-known paper.
I've heard of it. I mean, I heard the news, but I was busy doing other things at the time. I didn't pay much attention. It's fine.
And both AMD and Intel, both AMD and NVIDIA have added support for bfloat 16. And then I believe the latest ARM instruction set also added support for it.
Okay. Yeah, someone threw it on the link even today, right? And the new Vision or something came around, our AMD new Vision. AMX.
Well, that's Intel.
I can see that Wikichip cites Google's experiments, but I cannot see the link to the paper. They do cite the keynote talk about Google TPUs.
So ARM definitely is announced support. That was the link you threw in already. Fine. Well, what else?
Oh, and they compared it with half as well.
What's half?
Half, 16-bit IEEE 754.
Oh, 16-bit. No, IEEE 754, 16-bit version. Oh, yes.
Right, so half is, hang on.
It probably is a little more thought put into the breakdown between mantissa and exponent, whereas B16 was like just chopped off the bits.
Yeah, so I posted the a link to, I stole the code from Stack Overflow. But,
Matt, there's no link there, which maybe you just said you had no link for it. And here's your discussion about the breakdown, right? And here's the bits and precision. Yeah. Right. So it's a different breakdown in how they do bits as opposed to just chop. And Google's approach is very pragmatic. Let's see what happens. The answer is, oh, nothing bad. In fact, some good stuff. So chop's easy, quick, done. Yeah. There's a link. I got way too much reading now. And it's neural nets. Maybe that's the end of all other machine learning. I find it hard to believe, though.
Well, instead of reading it yourself, you could always have your computer analyze it.
Yeah, I saw this good Twitter, discussion in 2000, 2001. There was a what AI will look like in 20 years, right? And it's going to be these cyborg robots, Terminators taking over the world. And what it actually is in 2021 is there's a picture of a cat, and the computer's carefully labeled a dog, right? And this is the state of the art in AI. So I'm not yet afraid of our AI overlords. And no flying cars, and no moon colony.
But we do have a convertible in space.
I'm sorry, we do have a... And billionaires will be billionaires.
There's another one, like in the 50s, like scientists talking about, oh, let's go to the moon, and scientists in 2020, for the last time, the Earth is round.
Oh God. Oh. Well, I thought that was excessive until Trump got elected, and then, yeah, no, we've stooped to a new low. Wow.
Still stooping.
Haven't found rock bottom, is that what you're telling me? Yeah, Trump's trying hard to dig his hole deeper. That's for sure. Wow. And he's trying to drag down as much of the country as he can as he goes.
Wow. It seems to be the, what he learned from managing casinos. If you're going to go out
with a bang. Yeah. And take everyone down with you. All right. And there'll be plenty of folks to blame other than yourself. Fine. Wow. Okay, on that note, on that cheery note, I claim that we should meet again next week as proof and evidence that there is a unit of sanity in the world somewhere, and we're not all falling down the rat hole of anti-vaxxers and flat earthers. I have a theory about anti-vaxxers, by the way, and it's called Darwinism. And that theory actually extends to a whole lot of Trumpites as well, who demand not to wear their masks in their high-touch, high-spreader events. So fine. 10 years from now, we may have, 4 years from now, we may have largely self-solved as a interesting collection of the US population, COVID bites them, I guess. Yeah. Vax, I coded on Vax. You're trying to change the topic to something enlightening and fun, as opposed to being...
Let's talk about the Pdp-8 instruction set.
I got to practice on it. I don't know if I ever coded on it, but that was it was an undergrad class. Here is the Pdp-8 assembly language. It looked very interesting. X88 was pretty darn close. That was down there.
Do you mean 88 or do you mean 8080?
I think I managed one time to get on an 8088 and code assembly, but maybe it was...
Because 8088 was just an 8086 with half the bus missing.
Maybe I'm talking about 80.
I think you're talking 8080, which is also similar to the Zilog Z80.
I did a lot of coding on a Z80. I did tons of coding on a Z80.
Because wasn't a Z80 a cheap clone of a 8080?
Yeah, and they added a flip register set side, and then they added a couple index registers to make it more exciting. And then there were a lot of extra things that didn't go on the first several generations of chips because the masks weren't good enough. And so those extra things were on the periphery, and they got optically warped and they failed. So that you could ask a question if your 8080 supported the following instructions, or it, threw it into a lurk. it basically locked up. You had to power cycle it. And then you had a good one or bad one that did or did not support these instructions. That was a well-known Z80 hack for a long time. Some years later, we started getting reliable use of those instructions, but we still had a startup sequence that asked the question, will this Z80 run these instructions? This was a fun company. This was a crazy thing back in the day. This was doing recognition equipment. They were recognizing hand reading for the post office and for banks on checks. They're looking at addresses, handwritten addresses, and handwritten amounts on checks. And I was doing the data entry side where the handwriting recognizer failed. But the handwriting recognizer would take a stack of envelopes or checks like this and feed them through at 60 miles an hour and would drop the stack like this. And so it was a full-time job just to pile in these things. And, big bank or the post office would have a dozen of these giant machines, and they were the size of a living room. And they would pound them through and then do reading well past what any computer hardware could do at that era. So Pdp-11 controlled the entire rack of machines, but the reading was done analog. And there was a font, and you could put in different fonts. And a font was, every character was a card like this that took a CDC breakdown 64 by 64 grid and had a resistor. And you would tune the font by shaving the resistor to increase its resistance. And there was experts in the company who would build the font by pulling a bunch out and putting so much in, and they would highlight. So you got to have stronger signal if you matched the character, but then they would fine tune by taking a knife and shaving the side of the resistor to increase its resistance by thinning it out. That was one character. And so a font was a rack of 32, 64 of these things that they would plug into the side of one of the boxes, and it would do an analog look and take the out of the 64 font characters, you would pick the highest signal that you got out, and that was your pick font, and you kept the character, the CCD camera character image for a human to go inspect later for picking up errors. So there was also the notion of you didn't get a strong read, so you'd flag it as we don't know what this character is. And you'd have to go in front of a human operator, but they would only pick the mistakes out. And I was doing the software for having human operators update the mistakes. Mostly it was 99.9% accurate. It was pretty damn good. And you ran, it was freaking analog.
So since we're talking Z80s and stuff, one of the interesting trivia questions is, which is the most popular Intel chip?
Oh, Z80?
i960.
Why? Most popular?
Because they still sell more i960s than everything else they make put together, if I understand correctly. Yeah, and that chip is from probably before I was born or something,
Oh my God.
It's an old chip.
Wow. Well, I know Z80 went, you can still get them. They went super popular.
And you can still buy some 6502 derivative as well.
6502. Yeah, I coded on that as well. A friend across the street had an Apple II and 6502 assembly. There was.
That's where I learned assembly. Yeah.
There you go. Yeah. Wow. Okay, now we're dating ourselves. All right. Successfully enlightened the conversation to old parts talking about old stuff. It's all good. Same here. Now, Matt, 8-bit Atari. Yeah, okay, fine.
So that's why when I put up Java bytecode, it was like, oh, this is easy. We got JSR, we got RET, it's like,
yeah, right.
Back to normal.
Yeah, it was much simpler. It's kind of like I have sympathy for the next generation coders that came after, because life got way more complicated for all these things. When you wanted to do graphics, just flow a bit, you wrote to some memory location and you saw it on the screen. And you could just poke with BASIC and see the bits on your screen as you poked.
So Arthur and Jorn have to ask the CPU, which instruction set do you support before they can do anything?
Well, yeah. 1 billion instructions, all shady variations of not quite the same. Yeah, it's incredibly more difficult. Fine.
I think I'm kind of the opposite. I remember the first time writing assembly, we already had to pass the M32 flag specifically to switch to 32-bit architecture.
Yeah.
Because the default was 64, I guess.
Yeah.
Yeah.
Looking at your picture, I'd claim you're about 12, maybe 14 for the beard.
So it's even crazier, Jorn, because when you were writing a boot sector program to launch an operating system, you actually had to flip it into 32-bit mode from 16, because until UEFI, all Intel's booted in 16-bit mode. In fact, if you're doing a load from BIOS, it's still 16-bit mode when it hits the boot sector.
I think because the X86 chips originally were 16-bit, right?
That's correct. And in fact, there's no 16-bit instruction to go to 64, so you actually now have to go 16 to 32 to 64.
They were 8, then they went 16. They were the pre-generation, like the 8086 was the 16-bit version of the 8080, I guess.
That's correct. And
Yeah,
then
that's
the
why
88,
I mean
and then the
86.
8088 was the cheap version of the 8086.
Yeah.
Right, which had double cost instructions because it had to cycle things twice for having half-size buses or something. I remember some game going on like that. All right. Well, we've been shooting the history bits here for a while. I'm going to declare victory, and it was actually kind of fun, and I definitely learned a bunch of stuff here, like the analysis, the level of analysis for resource-aware analysis has gotten way the hell better than I've been aware of. So that's really cool. It's fun, as always. Hope to see people next week. Have a merry holiday season if I don't. But I think I'll still be on next week for sure. Christmas Day before, maybe not. I'll figure it out when I get closer, but I'll probably abort on Christmas and be around the day after, the week after. Okay. See you people next time.
Cheers.
Bye-bye.
See you next time.